Hello, everybody. Welcome to our special tour of the whole of planet Earth. I am Michael Hamburg. I will be your guide today, and I am very pleased to share our planet's history with you. So, we're going to hit some highlights about its birth, its evolution, why it's habitable, our place in the great scheme of things here. And most important in today's headlines is what is the future of our planet as our home? And we will start in about a second. So everybody kind of get ready. If you have questions, please remember there are no stupid questions. There are just unanswered ones or unasked ones. And I'd be happy to answer as best to my ability, either during the course of the tour or we're going to have a pause in the middle. And then maybe we'll have some time at the very end. And I will try and get to everybody questions. So if everybody is ready and you've got your walking shoes on, we're going to go enter the hall of planet Earth by one of our main entrances, and you'll see in front of you our half globe of our dynamic Earth. We will pause a couple of times at that, and I'll explain what that actually represents. So we're going to begin at the very beginning. So about 14 billion years ago, there was a universe born, and then fast forward about 9 billion years, a new star and its planets and moons came into being through something called the solar nebula. And we see that our planet has quite a history. And how do we know that? Because we have visitations from some of the leftover pieces that come to the Earth, survive the fiery descent through the atmosphere, and land on the ground and are known as meteorites. And the three specimens we're looking at here represent three different types of rock that have come to compose the anatomy of the Earth. So we're looking at here a kind of what's known as a chondrite. It makes a lot of the crust of the planet, and if we will get a closer look at it somewheres down the line here, there are little inclusions, little things embedded in there, minerals like calcium and aluminum. The second one seems to be a remnant of the insides of the mantle of a small planet. This is kind of a cooled magma. Could be from Mars. It could be from the dwarf planet Vesta, where we've gotten a lot of our meteorite samples from. And then we're going to look at number 3, which is the rarer type of meteorite. This is an iron meteorite, which comes from the very central cores of planets and planetesimals that have undergone a process known as differentiation, where through processes of heat and convection, materials kind of find different layers within the sphere, where the heaviest materials are in the center and the lighter ones are in the middle, and the lightest materials form the crust of the planet. And these three represent that process of differentiation, which is reflected in our home planet anyway. And we will see the composition of our planet is very much in part the knowledge is from these meteorites. There's a vast swarm of them around the sun between Mars and Jupiter. And it gives us this pie chart of what we have. And you can see here most of our meteorites is iron in the core. There's silicates, or basically silicon dioxide, which you find is common sand, makes up a lot of the crustal material. And various mixtures of rock make the mantle, which is a molten kind of the consistency of porridge. It's a rock that's heated so that it's bendable, it flows, and will play a great part in our next discussion of what makes the Earth breathe. And so again, here is our density samples. And if you were at the museum, you can actually lift these samples up. They are all the same size. They have the same volume of material, but to the touch, you would know that the core, which is iron, is very heavy. The mantle, which is above it, is a little less heavy. The crust is the lightest. That's what we walk on. And then there's the oceans, the water. And this is something known as density, which is basically the amount of material per volume. And here we will go and see passing that will come to the banded iron later. And we're walking towards the one of the newer parts. Now, the hall opened up in 98, 99, but then was upgraded in 2018 to add this convection model. So although this looks like kind of in an anatomy class at some post-mortem, this model is a real cross-section of our planet's engine. What makes the Earth dynamic? So in the center is a tremendous molten ball of iron surrounded by, the center one is actually solid from all the compression, surrounded by a molten ball, and then generating tremendous heat from three sources. One, the original accretion of the planet back 4.5 billion years ago. Second, you think of all that material, the compression bearing down towards the center heats up the material. And then there's the decay of certain radioactive elements like uranium, thorium, and potassium, all giving this engine a heat source. The heat wants to go someplace. It wants to rise. So there are cracks and fissures and vents and tubes all throughout the Earth's mantle, where this heat rises in the form of magma. They'll come out in volcanic eruptions, or they'll come out in mid-ocean ridges as the plates, which we'll talk about, separate, giving us an opening. This hot magma rises, and as it does, it cools, and then it sinks back down again, only to be heated and keeps coming around in a closed loop. You can picture this if you boil water in a glass Pyrex pot or something. You watch bubbles rise. The heat starts to dissipate. It cools, and then the bubbles sink, and they're heated again, and you get this closed conveyor belt, this dynamism called convection current. And what it does is that it brings up minerals. It brings up gases. It creates a new refreshment. So watch what happens to the surface during this convection thing. And we'll talk a little bit about what this looks like. This is called plate tectonics or continental drift. And if you had a GPS, it would not work back hundreds of millions of years ago, because the world did not look the way it does today. So watch where the continents start moving around on this magma. And until fairly recently, a few million years ago, it's kind of unrecognizable. But I think everybody could remember looking at maps, I know I did, and saying, this bulge of Brazil seems to fit into this indentation in Africa. And of course, it was poo-pooed for most of the formation of this until the mid 20th century, when this man was Alfred Wegener. He was a German meteorologist, polar explorer, and he came up with this notion that, these continents are on the move. And if you kind of go backwards in time, you can see how they once fit together. Now, right there, you can see how that South America and Africa, now they're kind of spreading, something called divergence. Plates are moving. But don't expect to feel it, because this motion is about the same as the growth of a fingernail. And I guess it's a good thing. We wouldn't want to have the ground under us shaking too much. Of course, when pressure releases a great amount of energy, we'll have earthquakes and things like that. So that is Alfred Wegener's work, plate tectonics. So what does that mean? So we're going to stop here at the Great Bronze Globe. This is a beautiful model. And if you remove the water and the air and the vegetation, you have this kind of topographic map of the Earth's basins, everything there. You can start to see some of the continents. There's North America we're coming in. It almost looks like the land, except some of Florida is underwater, and we're crossing the Pacific, where there are, many hot spots and sea mounts. These are submerged mountains, and we're crossing Asia here. And we'll get a shot here where we're going to see the subcontinent of India pushing up against Asia and creating, of course, the Himalaya mountains. Parts of early continents underwater. Great question, Anna. I would think yes, because the levels of the seas change. They've come and they've gone. And we'll see at the end of this, we're going to see that it might actually engulf all of us. So there's the Himalayas. You can see that big ridge up there. That's India having pushed into Asia. And then on the upper left, there's the Eurasian plain. We'll come over Africa. We're going to cross the mid-Atlantic, where you'll see ridges of mountains, the mid-Atlantic ridge, where plates are diverging or spreading. And there is North America. Once again, it's great when visitors are here to actually show them, can you find where you live? All right, and that globe has an exaggerated verticality of about 2.25 times. So how do we know this stuff? How do we know it? So I think it would be a good idea maybe to pause for a second here, just to give a little backstory of what we know and what we don't know. So this might be a funny story, but up until the mid 18th century, the latest word on how old the Earth was formulated by the Archbishop of Ireland, one James Ussher. What he did was he counted all the begats in the Old Testament, and by some calculations, he came up with the birth of the Earth at the 23rd of October. I think it was 9 p.m. in the year 4004 BC. Now, we may laugh at that. I mean, the Earth being about 5,500 years old, we laugh at that now, but it was taken quite seriously. This was the scientific word until a wonderful polymath, a Scottish doctor, mathematician, he went on hikes to east of his beloved Edinburgh, especially to this point called Sychar Point, and he contemplated these cliffs. And this is these are a cast that the museum did of the actual cliffs. I think this is an amazing job that they did. And what he saw here were these horizontal layers of red sandstone, just kind of one on top of the other. And yet, and here's a map, you can see where Sychar Point is, that little jutting point out there. This was in the mid 18th century. And he said, there's something about this that seems to tell me about time, that what's on the bottom, and you'll see what's on the bottom, a different kind of rock, a gray slate that is a metamorphic rock that came from clay and volcanic ash, is on the bottom, and having undergone some type of motions, thrust up, tilted, eroded. So we'll get a shot of that gray slate as the camera comes in, and then maybe a little more than 100 million years later, this red sandstone was deposited. This red sandstone was deposited on top of it. So he says, my God, this is a historical record of time, of what was happening in what we now call deep time. So James Sutton is considered the father of modern geology and gave us this great key to understanding this past of the Earth by reading the rocks. We can tell not only by the positions of the rocks and the compositions, but what did the atmosphere and what did water do in interacting with these rocks. And one of the nice things I like to think of is if you ever take a trip, and you're on a highway and the road goes through what's known as a cut, where the engineers have blasted out a hill, and you look on the side, you can actually see some of this history in rocks. There are actually books that were printed about for tourisms. So here we are at the dynamic sphere, and what this beautiful model does is that it removes layers of water and air and vegetation, and eventually it reveals the actual basins, the solid basins of the Earth. And we could see some of the continent. You can see as this thing turns, but it's a reminder how dynamic this planet is. So what will be the future map of the Earth, Dr. Poria? So that is a good one. I can't tell you that right now, but we know that it will be different. So I'm going to advise you to, at some point, upgrade your GPS maps, and we will then, you won't get lost. But they will be different. I think you may look that up someplace where there is a projection, although we don't know for sure what's going to happen. What more importantly is that the oceans are rising, so that's what we're going to see. And there you can see with the water returned, some of the continents there. It's a nice place to sit under. There's seating. You can contemplate there. So Brady has asked what the atmosphere is made of. So it's primarily nitrogen, about 80% nitrogen and 20% oxygen, with some trace elements of argon and carbon dioxide. And we'll talk about that because we're going to come right up to the history of our atmosphere and why it's so important. And there's some surprising facts. This beautiful piece of specimen here is known as banded iron. It's about 3.5 billion years old, comes out of the province of Ontario, and I would love to have countertops made of this thing. I think it would be beautiful. It's been polished. And what does it represent? Well, you know that tree rings show the growth of trees, and we're going to see that towards the end here. Here we see these horizontal layers of a type of mineral known as iron oxide. The gray is hematite. Hematite is interesting because it was also found on Mars. The red is a beautiful gem mineral called chalcedony. It is a gem mineral. And what we're seeing here is an interesting history. If you went back, and maybe we can pause here too for a bit. If you went back 2.5 billion years ago, you would be in trouble because you couldn't breathe the atmosphere. There was no free oxygen. All the oxygen was in the oceans and the seas. And upwelling from these vents from the mantle were all of this heat and energy. And what happened was that the oxygen dissolved in the oceans would chemically bond with these minerals, a lot of dissolved iron, and create these oxides. All right, we know them as rust commonly, and these two are particularly interesting. This hematite and chalcedony, and they would be deposited in these layers as most sediment is. And for a couple of billion years, this was happening. What happens when all the iron is finally bound with the oxygen is what will be the next chapter in the story. So we can resume the tour here and take a look at one of the agents that we're going to be very grateful for allowing a breathable atmosphere. And it's a little surprising what it is, but I always give thanks when I think about that. So we're going to look back, take a little how beautiful this is. You can see the cracks and the fissures that this thing underwent, but mainly those beautiful red and gray bands. It would be nice to have one of those as as a paperweight or something. So when we go around the corner, we're going to look at a very interesting microorganism called a cyanobacteria. So with the creation of life, which we will also talk about, the proliferation of colonies of cyanobacteria, they developed a tremendous process, which we take for granted now, called photosynthesis. The yellow thing in front of us here is a petrified stromatolite. And the stromatolites, well, think of them this way: these microbes that were producing oxygen through photosynthesis. Now, the oxygen already was bound up in these iron sediments, so it had no place to go but the atmosphere. So for many millennia, this oxygen was being released into the atmosphere in an event we call the Great Oxygenation Event. And by the time about 500 million years ago, life had exploded in what is known as the Cambrian explosion due to the action of these small one-cell creatures. Now, they lived in giant housing projects. They would take mats of mud and they would layer these mats of mud and they would produce the oxygen. And then there was more sedimentation, and then they died, and then they were compacted, and then they were lithified or turned to stone. And here is one that was taken by the museum and cut and polished. They're quite beautiful as just specimens there. And we have another one to the right, another smaller specimen of the banded iron. And we can actually see a recent colony of stromatolites from Sharks Bay in New South Wales in Australia. And there are some that are still alive and producing oxygen in these places. So I have a question from Manito. How does Earth make all those rocks? So there's a process basically called accretion and lithification. You take small particles and you glom them together. They get bigger. Sometimes they collide, and in the heat of collision, they stick together, and they just get more and more massive and dense. And you wind up having different types of rocks. You have crystalline rocks. You have types of rocks that have been underwent different changes. They become metamorphic. Some rocks are volcanic, and they are known as, they're done with thermal processes. And here is a rock also found in Australia, of a mineral called chert. Now, chert is an interesting mineral because it is very, very much indicative of processes that are known as diagenetic, or involving change with life in it. And this might be a fossil, one of our oldest fossils. It's a little hard to see because it's dark in this one, but we think that there is a microbial fossil that could be 3.5 billion years ago. One of the things researchers are doing is that they're pushing back the origin of life further and further as our discovery techniques are getting more refined. So if when you get a chance, you could take a look at that closely. And okay, so we're passing our beautiful globe, and you can see the seating area down in there. So if you ever get tired when you come, by the way, there is limited capacity for in-person visits. Many of the halls are still open. So we're going to really now take a look at one of the profound questions that people have is, why is the Earth habitable? What makes this planet the only one that we know of in the vast cosmos that we're just beginning to explore, the one that has life on it? I'm not saying it is, but as far as we know right now. So everybody knows the old joke about the store owner who's asked, "Why is your business so successful?" And the guy says, "3 reasons: location, location, location." So that really applies to the Earth also. We are at the right distance from our parent star in what is known as the habitable or Goldilocks zone. Not too hot, not too cold. I also would like to mention somewheres here, we'll put in that the presence of a large moon has helped things on the Earth. We also have a protective shield in a thick atmosphere, which blocks a lot of either objects like asteroids and meteoroids, cosmic rays reflected by the ozone layer, the right temperature, which is neither hot to or cold. I mean, Venus is halfway to the melting point of lead, and Mars is pretty cold. We have water. I mean, why we have liquid water is because where we are at that place where water can stay liquid and remain liquid, pressurized by the atmosphere. So that brings us to the question of life. How did life begin on Earth? Well, I'm going to confess I don't know the exact answer. We know pretty much where. Well, there are 2 schools of thought about that. We're going to look at one of them, and we pretty much know when. And again, as I said, we're pushing that back. Here's a core from the seabed, which we see has a lot of little chambers in there and places that perhaps nature used as laboratories for experimenting. Again, we don't know that. There was an experiment back in the 50s by Miller and Urey trying to recreate that. Nothing conclusive. These objects here, known as sulfide chimneys or black smokers, are really interesting. These guys were harvested off the Pacific Northwest of the United States about 20 years ago, named Godzilla. And they represent an interesting phenomenon. So remember, this magma under the crust is hot, and the heat wants to escape. So there are fissures in the crust, even below the ocean. Water pours into that, superheated, gets shot up as steam. Sometimes it could reach 700 degrees Celsius or 150 degrees. I mean, 700 degrees Fahrenheit or 300 degrees Celsius. This superheated water has a lot of dissolved minerals from the mantle, hits that cold water again. All of those minerals start to precipitate. They start to build this mound, this chimney. This one was about 20 meters high and had to be cut and brought to the museum. So what's the significance of that? Well, we look closely at these sulfide chimneys, and we know that there are bacteria that love iron as a diet. And these bacteria then become food in the next chain, and small fish get eaten by a bigger fish. And you'll see in a video here that some of these hydrothermal vents where these chimneys are the locations of thriving biospheres of animals that never see the sun. No photosynthesis, but something instead known as chemosynthesis. There's a chemical process that creates metabolism, that creates life. Again, filled with small chambers, protected from the outer environment. Again, perhaps nature's petri dishes. Here's a video of present-day thermal vents, and you can see the black smoke coming out. This is the mineral, the sulfides that are being precipitated when it hits the cold seawater after being superheated. We have a couple of shots here. You'll see of animals coming, and they're not primitive either. We have these giant red tube worms. We have things that look like crabs. We have something that you'll see here, a picture of a fish, a ray of some type. And the implication is, well, maybe you don't need direct sunlight to harbor life. There are some moons in our solar system, like Enceladus around Saturn and Europa around Jupiter, that we believe have sub-ice oceans of liquid that may be heated by tidal tugging. And if that's true, so the smoke, Stacy's asking, the smoke is actually the precipitation, those sulfides that are being precipitated. They're coming out of solution when they hit the cold seawater. And that is why they're known as black smokers. There are also white smokers, which just show a different type of dissolved mineral in it. And so this is the only light that these guys have ever seen, is the searchlight on the submersible. There's that ray that I was promising you before. Far from a unicellular simple organism, that thing is a complex animal. And there we found it. This was not known a generation ago. So maybe we'll find this on other worlds too. That would be pretty exciting. You know, we will see that. So that's the sulfide chimneys, the smokers. So let's kind of move towards what's happening now. It'll give us an answer. Somebody asked before, what does the future have for us? So here is an example of a coral. Now, coral is an interesting kind of a multi-organism colony, and they live usually in tropical waters. The Great Barrier Reef off the east coast of Australia is famous for its coral reefs. And if anybody is a snorkeler or a scuba diver, you can attest to how beautiful they are. This one's dead. It's bleached. What's happening here is that with increased carbon dioxide emission, it gets dissolved in the water. It acidifies. It creates a weak acid, carbonic acid. That coupled with warming of the oceans is very bad for corals. So we do know what's happening the past 100,000 years in terms of the climate. Here's an ice core taken from Greenland that represents the last 100,000 years of climate. The bands again there, if you would see, this core has been laid horizontally, but it is a vertical thing. And you can see that the clear ones were taken in the summer, and the dark ones were the winter. And we can tell just by either the thickness of it, the embedded materials, what was going on in the earth at a particular year. So why are there holes in there? There are holes because, nothing's perfect, right? So maybe there was dissolved gas that finally came out and left a void there. That, of course, is a model. Otherwise, we'd need a freezer for it, but it's accurate. Also, everybody's familiar with tree rings. And so here we have two different types of things. The horizontal thing is called a tree core. You could remove a core from a tree without killing it and see what's going on. Because trees are so long-lived, they are a perfect record of what was the growing conditions, what was the climate. This one here that you see here is a kind of an oak that it started growing in the 18th century, and the pins represent things. Here's the white pin. Well, we'll see the white pin is the oldest ring, and the yellow pin at the that was a drought. The next one down was a severe drought. And finally, the tree dies in, I think it was the mid 20th century or something. I quite remember. And that was it. So our jewel in the crown is our latest edition, and that is our climate wall. Some of the best resolution videos telling us what's going on in the world. So what it can tell you here is that we're tracing storm systems first. You can see here, the lights are also, we'll talk about the energy used. But for the past few years, since 2018, we've had some fierce hurricanes and typhoons. We've had big brush fires because the climate's changing. The patterns of the storms are changing. Where there were droughts, there are floods. Where there are floods, there are droughts. The energy is just changing all over. And most of it, as you'll see, comes from human activity. Yes, there's been always natural climate change, but not to the extent that we see here with the complete complete emissions of carbon dioxide and other greenhouse gases like methane and water vapor. So it is definitely a warming world. We are looking for a way to switch from fossil fuels, which is the main source of that, but it's become politicized, as we all know that. And it's a shame that science becomes politicized, but I won't editorialize anymore. But if we trace I have a manual's asking if the hurricanes become stronger, will they be more frequent? That's a possibility. They will become more frequent. They will hit places that they normally hadn't before. So we're looking here at a graph that's showing the CO2 levels in the atmosphere, parts per million, and it's pretty steady. We can see the beginning of the current era at AD1. And then, of course, something very dramatic happens. You can see at the beginning of the Industrial Revolution at the mid-18th century, my God, look at the spike, look at the rise of that. And it's not abating. Although during this pandemic, what was shown is with the shutdown of transportation and a lot of industry and travel, the atmosphere was getting cleaner and cleaner. So the answer is obvious. We're putting a lot of what we call schmutz into the air. And if we can take it out, we will be in better shape. And it's so hard to deny or avoid that. And we use a lot of energy. We're just using a lot of energy. And what are we going to do? Because the new, the short-term effects will be rising sea levels and all the storms. But the long-term effects, what happens? Do we lose our coastal cities? If you live in a coastal city, do you have to tie a boat up to a 14th floor apartment? So Yasmin is asking, if hurricanes become more frequent, what about tornadoes and earthquakes? Oh, assuredly, any kind of storm now, because not only will the oceans be warmed and changed, but the atmosphere will undergo. And about tornadoes. Tornadoes get their energy from heated air. It's quite dramatic. Earthquakes, I'm not so sure so much about earthquakes, as that more depends on plate tectonics. But sure, why not? We can expect a kind of a rough future if we don't get a hold of that right now. So I will take, as we can see here, back at our contemplative dynamic Earth. I want to thank everybody for walking through this with me. And if there are any more questions, I'd be more than happy to try and answer that. Okay. What is the longest and biggest coral reef? To my knowledge, and I have to admit, I'm not an expert on coral reefs, but I think it is the Great Barrier Reef off of Eastern Australia. I think that if somebody wants to chime in, if that's not right, please feel free to. Okay, Ro. So this is a hall that I said opened up part of the Rose Center for Earth and Space, which opened up in the last years of the 1990s, along with the Gottesman Hall of Planet Earth. But it was, as I said, updated in 2018 with the addition of the convection model and the animations that are in there, and the climate wall, which really draws a lot of people. And I always end tours with that as saying, this is the cautionary tale. Don't despair. Do something about it. What can we do? Any other questions? Okay, Dr. Puria. So global warming, yes. Well, here's the thing. Given the records from the ice cores and the tree cores, we know that the Earth has warmed and cooled over the billions of years it's been around. But as you saw on the climate wall graph, nothing has changed so drastically as the change since the Industrial Revolution. I mean, remember, that graph went almost vertical past 1750. So yes, we are definitely doing it. Yes, I mean, the sun has changed in its output. The Earth has changed. We've had ice ages and whatnot and tropical ages, but nothing to the extent of what we're doing right now. And David is saying, I don't think there's anything we can do about. Oh, David, don't give up. We can do something about global warming. I mean, there are small changes. There is promises from the auto industry about really trying to make a goal of all electric vehicles within the next couple of decades. The search for renewable fuels, solar, wind, things like that. I mean, it's not easy. There are interests. There are interests that want to protect, the oil industry, the gas industry, and things like that. So we have to be positive about it, because otherwise, why give up this wonderful evolution? We saw this evolution from a planet of nothing to a planet of complex biodiversity, with human beings able to understand it, and getting better and better at it. I would hate to see that give up like that. Okay. Anybody else? Anybody else? A question? Well, if that's it, I want to thank everybody for coming along with me. I hope you got a better understanding of the history of our planet and its future. Please, if you can, visit the museum, even though it's limited capacity. You can still come in with, advanced tickets, and you can see some of this at your own leisure. I had to kind of just give you the highlights in this time frame, but it was quite enjoyable. And come back, and come back. Thank you very much.